So, today we will continue our discussion with the example of distillation column. Again I am drawing the schematic of the distillation column. This is the tower. Now, feed is introduced in the feed tray. Feed flow rate is F, composition is Z. Then the overhead vapor left the top tray and then that is condensed in the overhead condenser. The condensed liquid is then accumulated in this reflux drum. This is the reflux drum. This is condenser, this is reflux drum. Then a part of this liquid is taken out as distillate. This is the top product with flow rate D and composition XD. Now, another part of this accumulated liquid is recycled back to the top tray. This is the top tray. So, this is the connection for the reflux drum, reflux rate, and the bottom liquid which left the bottom tray, this is bottom tray, is reboiled in the reboiler. This is the reboiler. Then the produced vapor is recycled back just below the bottom tray, fine, and a part of the liquid is withdrawn as bottoms. This is the bottom product which has the flow rate of B and composition of XB. We have discussed with this example and one control configuration we have drawn in the last class. That control configuration was the feedback control configuration. That was the feedback control configuration, fine. In that feedback control configuration, we have measured XD. Basically, for this particular process, the controlled variable is XD and corresponding manipulated variable is reflux rate. This is reflux rate, fine. We are considering only the single loop at the top. We are not presently considering the bottom loop, fine. Now, in the feedback control configuration, we have seen that the controlled variable which is XD was directly measured, fine, to manipulate the reflux rate. Today, we will consider another control scheme, that is feed forward control scheme, fine. First, we will configure this feed forward control scheme for this distillation column. In this feed forward control scheme, the disturbance is measured. Here disturbance is the feed composition as well as feed flow rate, but we are considering this is the measured variable. Now, for measuring this feed composition, we need one composition analyzer. This is composition analyzer which is measuring basically the feed composition Z. We are assuming that this composition analyzer output is exactly identical with the feed composition. Then this information Z goes to the feed forward controller. This is the block for feed forward control scheme. Then this feed forward controller calculates the control action based on this feed composition, and this controller action is implemented through this control valve. Fine. For the feed forward control scheme, disturbance variable or load variable is measured using one composition analyzer. Then that measured feed composition information goes to the feed forward controller. Then the controller calculates the control action, and that control action is implemented through this control valve. Fine. So, the major difference between the feedback control and feed forward control is, for the feedback control scheme we measure directly the control variable, and for feed forward control scheme we measure the load variable or disturbance variable. There are many other differences which we will discuss in the subsequent classes. Fine. Another control scheme we will discuss next with this distillation example, that is inferential control scheme. So, we will consider the same distillation column to discuss inferential control scheme. This is a schematic of the same distillation column. Feed is introduced here, then the overhead vapor is condensed and condensed liquid is accumulated in the reflux drum. A part of that liquid is recycled back to the top tray as reflux stream, and a part of the liquid is withdrawn as distillate. At the bottom section we incorporate one reboiler. The vaporized stream is introduced just below the bottom tray, and at the bottom product is withdrawn. Now, in this inferential control scheme, the XD, which is controlled variable, is not directly measured. Fine. Most composition analyzers provide large delays in the response. Secondly, it provides high investment and maintenance cost. That is why sometimes this composition, I mean the product composition, is not directly measured. In that case, we search for the secondary measurements. Fine. And then using those secondary measurements, we can infer the product composition. That is the purpose here. So, to estimate XD, we need to select the secondary variables. For this particular example, suppose this is first tray, this is second tray, this is third tray. So, the temperature of this first tray is suppose T1, this is T2, this is T3. It is quite easy to measure the temperature compared to the composition measurement. Fine. So, we can say that these three tray temperatures we can consider as secondary measurements. Fine. So, we will measure these three temperatures using thermocouples. Then here we put one block for estimator. These three temperature, after measurement, the temperature information goes to this estimator. This estimator basically nothing but one algorithm which consists of some equations and correlations. These correlations basically calculate the XD based on the information of the measure temperature. Fine. So, here some mathematical equations are included within this estimator, and using those equations we can directly calculate based on this measure temperature information xd value. Fine. Basically, this composition is inferred based on the measure temperatures. Then as usual, this estimated composition xd goes to the controller, and the controller calculates the action, and those control actions are implemented through this control valve. Fine. Since the composition, product composition, which is the control variable, is inferred, that is why the controller is called inferential control. Fine. So, we can write that the unmeasured output basically is the function of secondary measurements. Here the unmeasured output is xd, and the secondary measurements are 3 temperatures, T1, T2 and T3. Fine. So, I have mentioned earlier that why we prefer this control scheme, inferential control scheme, because if we directly want to measure this product composition, in that case we need composition analyzer, and most composition analyzers provide large delays in the response. This is the first drawback. Most product composition analyzers provide large delays in the response. Second drawback is high investment and maintenance costs. This is the second drawback for the use of composition analyzer. Fine. So, this is all about the different control configurations for the with the example of distillation column. In the next, we will discuss the different hardware elements of a control system. We will discuss different hardware of a control system. To discuss this topic, it is better to take one example. We will continue the heating tank system. To discuss this topic, it is better to consider one example, and we will continue the heating tank system which we will discuss in the first class. This is the heating tank system. Feed is introduced with a flow rate Fi, temperature Ti, and product is withdrawn with a flow rate of F and temperature T. Now, to heat the liquid in this tank, one steam stream is introduced with a flow rate, suppose F suffix St, and for this particular system we have this control pair, I mean controlled variable and manipulated variable pair. We want to maintain the temperature through the manipulation of steam flow rate. Fine. Our control objective is to maintain the temperature of this tank, and that is why this is our control variable. Corresponding manipulated variable is steam flow rate. So, this is basically a closed loop system. I mean this is the open loop system. If we want to make it close, we need to include the control scheme. Fine, this is open loop. Now we want to close it by introducing control scheme. So here temperature is the control variable. So we need to first measure the temperature by using one thermocouple. This is a thermocouple. Then this measured temperature T goes to the comparator. This is the comparator, where the measured temperature is compared with the desired temperature. This is positive, this is negative. Output of this comparator is the error signal. Then this error signal goes to the controller. Then the controller calculates the control action, and that control action is implemented through this control valve. So this is basically the closed loop system. Fine. Now we will discuss what hardwares are involved in this closed loop system. So first one is the process. First one is the process. In this process, physical and chemical operations occur. In this process, physical and chemical operations occur. This heating tank system is a process. Fine. This is the first hardware involved in this closed loop system. Second hardware is measuring instruments. Measuring instruments or sensors. Fine. These measuring instruments or sensors are used to measure. These are used to measure. First one is load variable. These sensors are used to measure control variable and secondary output. Third one is secondary output. Although we have shown here only the measurement of control variable, but we can measure also the disturbance variable and secondary output by the use of the measuring device or sensor. So we will just discuss in brief what are the different measuring devices used for different variables. So we can write them in a table form: variable and sensor used for measuring that variable. Like first variable is temperature. Say temperature we can measure by the use of thermocouple. Fine. We can use thermocouple, we can use resistance thermometer. We can use thermocouple for measuring temperature, we can use resistance thermometer, but mercury thermometer is not good because the measurement cannot be transmitted readily. Fine. Mercury thermometer is not good option because the measurement signal cannot be readily transmitted. Next we will consider another variable, that is pressure. Pressure we can measure by the use of manometer, by the use of diaphragm element. Fine. For measuring the pressure we can use manometer, we can use diaphragm element. Next we can consider another variable, that is a flow rate. Flow rate we can measure by the use of orifice meter. Flow rate we can measure by the use of venturi. So, these are two measuring devices which are extensively used for measuring the flow rate. Now, another variable is liquid level. Liquid level is measured by the use of differential pressure cell, DP cell. Liquid level in the tank is measured by the use of differential pressure cell. Another one is composition. Composition is measured by using chromatographic analyzer. Fine. Although we have studied all these things in the instrumentation part in details, but just to know which devices can be used for different variables, we have just discussed in brief. Fine. So, our second hardware was the measuring instruments or sensors. Now, third hardware is transducer. Transducer. Now, measurements cannot be used for control until they are converted to physical quantities. Measurements cannot be used for control until they are converted to physical quantities. Physical quantities, say for example voltage, say for example current, say for example pneumatic signal. Fine. So, measurements cannot be used for control until they are converted to physical quantities which are readily transmitted. These signals we can readily transmit. Fine. And this is the purpose of the use of transducer. Basically, the transducer physically convert the measurement signal to the physical quantities. Fine. Next one is transmission lines. Transmission lines. This is used to carry the measurement signal from sensor to the controller and from the controller to the control valve. The transmission lines are used to carry the measurement signal from sensor to controller and then from controller to control valve. If you see the schematic representation of the closed loop system, I think you can clearly understand this. Fine. So, this is the usage of the transmission line. Now, measurement signal is sometimes very weak. Sometimes the measurement signal is very weak, say for example in few millivolts. Measurement signal is sometimes very weak, for example some few millivolts. In that case, this transmission line is equipped with amplifier. Fine. When the measurement signal is very weak, in that case the transmission line is equipped with amplifier. This is the fourth hardware which is involved in the closed loop system. Now, fifth hardware is the controller. this is another hardware which receives measurement signal from the sensor. The controller basically receives measurement signal from sensor, fine, and then it decides what action should be taken. Based on the measured values. So, the controller basically receives the measurement signal from the measuring device, fine. In the next step, the controller calculates the control action based on the measured signal, comparing with the desired value of that control variable. Sixth hardware is the final control element. Final control element. Now, for the case of controller, I told that the controller basically calculates the control actions. Now, that control action is implemented through the final control element, implemented through the final control element. So, the control action which is calculated, produced by the controller, that is physically implemented through this final control element. Can you give any example of the final control element? Yes. First example is say control valve. Another example is variable speed pump. Variable speed pump. Variable speed compressor. Why variable speed? If the speed is fixed, then that cannot be changed. That is why variable speed pump and variable speed compressor. Now, next hardware element is the recording device. Recording device. This is used to visualize the plant behavior. This is used to visualize the plant behavior through the measurement signals, fine. If we wish to visualize the plant behavior at different situations, we need one recording device, and that realization we can achieve through the measured values. And for this purpose, we can use video display unit, which is usually accommodated in the control room. Video display unit can be used for this recording purpose, which is usually accommodated in the control room, fine. So, these are about the hardware elements for a particular process. So far we have discussed the first topic, that is introduction to process control. In the next we will discuss the second topic, that is the mathematical modeling, fine, and the use of mathematical modeling in process control. So, we will start to discuss the second topic, that is mathematical modeling. Mathematical modeling. First, we will know in brief what is the mathematical model. Suppose we have one experimental setup. So, we will represent the experimental setup we will use one block to represent this experimental setup. Now, to this experimental setup, the input is introduced. I mean, input is introduced to the setup. Fine. And if we run the setup, we get output. This is a common thing in our laboratory which happened. So, what is basically the model? Can we represent this experimental setup by some mathematical equations or correlations? We can. We can represent this mathematical setup by some mathematical correlations or equations. So, suppose some mathematics are involved, then we are giving the same input to this block. Fine. We will get some output. Now, this block is the representation of the model. This block is the representation of the model. Fine. We are just representing this experimental setup by mathematical correlation. Now, if these two outputs are close enough, then we can say that this model is a good model. Fine. If these two outputs are close enough, then we can say that this is a good model. So, model is the mathematical representation of a process intended to promote understanding of the real system. Model is the mathematical representation of a process intended to promote understanding of the real system. A real system we can represent by using some mathematical equations and correlations. So, this is the definition of model. Fine. And next we will discuss what is the use of this model, why we will develop the model, what is the use of mathematical model in process control, that we will cover in the next. So, use of the process model. First, we can write to understand the process behavior. To understand the process behavior. Fine. Suppose we have the model and we have the solution of this model also. We are giving some input to this model. We can get the output only if we have the solution, otherwise we cannot get the output. Fine. We have developed the model structure for a particular process. We are giving some input information to the model. Basically, the input information is specified, and then if we solve the model, then we can get some output. Fine. Now, suppose the model initially is at steady state. I mean, after startup we can reach at steady state. Now, at steady state we are giving some change in this disturbance variable. We are giving some change in disturbance variable. Then the process will shift from steady state to another state. Basically, if we change in load variable, we will get some transient response, and that transient response we can get by performing this simulation of this model without performing the experiment, isn't it? So, we can understand the process behavior by some change in load variable to understand the transient behavior without performing the experimental setup. Fine. So, this is the first purpose of the model. Secondly, to train the operating personnel. The model we can use for training purpose without running the experimental setup or without running the plant. Suppose we have the model structure same thing which we have drawn earlier. We have some input, we have output. Now, some situations can be irritated using this model, like the feed is introduced to a particular process. Here we are directly using some value for the feed flow rate. Now, suppose the pump is not delivering the feed to the process. What will happen? Suppose in the distillation column we have some minimum reflux rate. If we consider lower than that minimum reflux rate, what will happen? So, these types of emergency situations we can irritate by the use of this model without disturbing the process, or even some situations cannot be permitted to irritate in the real process. Fine. So, to train the operating personnel, we can also use the simulated model. The next purpose is selection of control pairs. Selection of control pairs. We have taken few examples and we have discussed the control variable and manipulated variable pair, but these control variable and manipulated variable pairs we can select by knowing the model of that particular process. Fine. So, if we know the model of a particular process, we can determine the pair between control variable and manipulated variable. So, for this purpose also we need the process model. Fourth purpose is to develop the model based controller. You know, most of the advanced controllers are model based controller, and the name clearly suggests that the controller which consists of or which includes the process model, those controllers are basically model based controller. So, most of these advanced controllers use the process model. So, in that sense we can say that we need the process model for the development of advanced controllers. Fifth one is optimize the process operating conditions. To determine the most profitable operating condition, we need the process model and economic information. Fine. So, we need process model and some economic information to determine the most profitable operating condition. Most profitable operating condition. So, we need the process model, we need some economic information to determine the most profitable operating condition. So, these are the issues for which we need the process model. Next, we will discuss the classification of process model. Classification of process model. There are different ways to classify the process model, but here we will discuss the classification of process model based on how they are obtained. There are different ways to classify the process model, but here we will discuss the classification of process model based on how they are obtained. Fine. There are three different models. I mean, we can classify in three different ways. Three different models are there. First one is theoretical model. The theoretical model is basically developed based on principles of conservation. This is developed based on the principle of conservation. Fine. So, first type of model, that is theoretical model, and this model is developed principle of conservation. I think you know the principle of conservation, like mass conservation, energy conservation, momentum conservation. Fine. And another type of model, that is empirical model. This model is obtained by fitting experimental data. The second type of model, that is empirical model. This empirical model we can obtain by fitting experimental data. Basically, if we have the experimental setup, we have different sets of input output data. Now, if we have the input output data, by fitting those experimental data, we can determine the coefficients. Fine. By that way, we can construct a model, and that is the empirical model. And third one is just the combination of these two, theoretical and empirical model, that is called semi-empirical model. Sometimes this is also called hybrid model. Semi-empirical model is the combination of theoretical model and empirical model. Fine. Semi-empirical model is the combination of these two. Next, we will discuss in brief what are the advantages and disadvantages of these models. So, first is the theoretical model. First is the theoretical model, which is developed based on the conservation principle. So, what is the advantage of this model? First advantage is it provides physical insight, into process behavior, This is the first advantage. Fine. Physical insight into process behavior. Second advantage is it is applicable for a wide range of conditions. it is applicable for a wide range of conditions. This is the second advantage. Similarly, what are the disadvantages? It is time consuming to develop. So, it leads to be time consuming to develop, because particularly for the complex systems the theoretical model is too large. So, in that sense we can say that this is time consuming. And another drawback is some model parameters are not readily available. Some model parameters, for example, reaction rate coefficient, overall heat transfer coefficient, these are not readily available. Fine. In that case, we have to follow the empirical technique. So, these are basically the two drawbacks and two advantages of the theoretical model. Now, what about the empirical model? I think we can say something for this empirical model based on the discussion of this theoretical model. So, what is the advantage? It is easier to develop. It is easier to develop. Fine. This is the advantage, because if you have the input output data set, then we can fit some correlations or equations using those input output data set. So, for a complex process we do not have so many equations like theoretical model. So, this is only the advantage for this case. And what are the disadvantages? Yeah, this is applicable for a narrow range of conditions. This is applicable for a limited range of conditions. Fine. So, this is the advantage, this is the advantage and this is the disadvantage for the empirical model. Similarly, I think you can find what are the advantages and disadvantages of the semi empirical model. Fine. Now, for the process control, we have discussed earlier different variables. I mean input variables, output variables, then input variables are again two types, manipulated variable and load variable, and output variables are two types, measured output and unmeasured output. At this time we will discuss another variable which is extensively used in process control, that is state variable. Fine, that we will discuss now. State variable. State variable basically describes the natural state of a process. State variable describes the natural state of a process. Now, there are basically three fundamental quantities. There are three fundamental quantities. What are these quantities? Mass, energy and momentum. These are three fundamental quantities. Now, these fundamental quantities are usually not directly measured. These three fundamental quantities are not directly and conveniently measured. And these three fundamental quantities are usually characterized by, say, temperature, by pressure, by composition, by flow rates, etc. There are three fundamental quantities: mass, energy and momentum. These three fundamental quantities are not directly and conveniently measured, and they are characterized by these variables: temperature, pressure, composition, flow rate, and these variables are called state variable because they describe the natural state of the system. So, these are called state variable, fine, and it arises naturally in the accumulation term. We will discuss in the next the conservation principle, and there we will see that the state variables usually present within the accumulation term. So, it arises in the accumulation term. Fine. Within the accumulation term, the state variable is present. And since we have discussed the state variable, in the next we will discuss state equation. In the next we will discuss state equations. These equations basically derived, these equations are derived by the application of conservation principle. On the fundamental quantities, to relate the state variables with other variables. Are called state equations. The state equations are derived by the application of conservation principle on the fundamental quantities to relate the state variables with other variables, including other state variables, are called state equation. These are about the state variable and state equations, and how we can see the state variable within the state equation. I mean, first we will go for the development of state equation, then we will see which one is the state variable within that state equation. Now, for that purpose we have to know the conservation principle. Fine. The conservation principle we can represent in general form like rate of accumulation equals to rate of input minus rate of output plus rate of generation. This is the general form of the conservation principle. Fine. Now, I told about the three quantities, three fundamental quantities: mass, energy and momentum. So, if we include here rate of mass accumulation equals to rate of mass input minus rate of mass output, that is the conservation of mass. For the case of conservation of mass, there is no existence of this rate of generation term, fine. And for the energy conservation, similarly we can write rate of energy accumulation equals to rate of energy input minus rate of energy output plus rate of energy generation, fine. So, this is about the conservation principle, and the state equation, state variable, the description on that, I mean by the derivation of state equation we will know which one is the state variable. This thing we will discuss in the next class. Thank you.